Now we want to talk about gas stoichiometry.
So gases are really our main topic. We want to really have this kind of molecular image that gases are, where we have that matter, where the atoms are really far apart and they're just randomly moving around. Whereas when we get to solids and liquids, in those cases, the molecules, the atoms are all touching each other and it much more restricts their movement. Whereas gases are really mostly empty space. There's a lot of space in between the molecules. So if you have a sample of gas, it's mostly a bunch of nothingness. And one of the real kind of implications that comes from that is because these molecules are really far apart, a lot of the different gases, it doesn't really matter what the molecules that you're looking at are. They're going to behave in similar ways, especially with how their physical properties change. That's why we have these named gas laws to look at how the physical properties, different physical properties of a gas are related to each other. Followed that up with the ideal gas law, where we're no longer looking at changes, but instead looking at particular states of a gas, right? Right now, you have certain conditions of a gas, the pressure, the volume, temperature, number of moles that are all related to each other. So these are distinct from the named gas laws where you can relate different properties to each other. So knowing the pressure, the volume, and the number of moles, you can figure out the temperature, right? And you can get information on a different type of physical property. But again, this is all for one state of a gas. So what we want to get into is, we talked a little bit about this using the ideal gas law in lots of the videos. We're going to talk about one more application of them, the ideal gas law, and that is that it allows us to relate volume for a given amount of gas. It's related to Avogadro's hypothesis, right? The idea that the moles per liter, right, that molar volume of gas was dependent on the conditions. And so we're going to use that in conjunction with stoichiometry. Say previously when we looked at stoichiometry, say this top reaction, where we were looking at, say, you have some aluminum oxide and how much aluminum oxide should you get in order to produce your target mass of aluminum, right? You have a solid becoming a solid, and we would describe those as using masses, right, as the amount of solid that you have. So when you start to do any sort of reactions dealing with gases or working with gases, we tend to think about gases in terms of their volume. So what volume of nitrogen gas would you want to use to produce a target amount of, say, any product, in this case, ammonia? So whenever you're dealing with gases, a lot of times instead of using mass, we use volume of the gas under given pressure and temperature conditions. So when we're doing the stoichiometry process, we know that when we're working through mass to mass, it's a three-step process, right? First, we do the molar mass, then we look at our reaction coefficients, and then the molar mass of whatever you're trying to turn into, right? So it's always the same three-part process. When we're looking at doing anything with gases, it's going to be the same idea, and usually you can still relate to mass and still use molar mass. You still need to use that molar mass because reaction coefficients relate moles to moles. And then finally, you want to get the volume of it, right? You want to get the volume of gas, so you use the ideal gas law. One thing to note, when you're using the ideal gas law to figure out the volume of a gas, you need to have the temperature and pressure. So this is similar to the fact that you needed molar mass as like your kind of conversion factor. It's the same idea where you need to know the temperature and pressure, what conditions your gas is under, in order to go from from moles to volume, to go back and forth between those to get whatever that sort of conversion is using the ideal gas law. Basically, you need those other variables in the equation. Let's take a look at an example. Airbag inflation is caused by sodium azide, which is NaN3. An airbag contains 130 grams of the NaN3. What volume of N2 gas is produced in one airbag at 1 atmosphere and 25 degrees Celsius? So if we start out trying to read the problem, parse it out, we want to think, what do we want? And we can see that what we're after is a volume of nitrogen gas. This is the kind of thing we've looked at before. We've dealt a lot with volumes of gases, right? We saw our named gas laws. One of the things to parse out right away with the named gas law, we would have some information about a different volume of the gas. There'd be indication of a change. There's definitely a change going on here, but it's a chemical reaction. It's not that you're compressing the gas or expanding the gas, heating the gas. You are creating gas, right? New gas is being produced in this chemical reaction. And what is the volume in that chemical reaction that's being made in that process. So when we want to get the moles, right, we know we're dealing with moles and then whenever we're dealing with stoichiometry, we need moles. And whenever we see a gas involved in there, we know that we're going to be using the ideal gas law with the moles, which is what plugs into our stoichiometry. So if we're going to use the ideal gas law, with stoichiometry, we always need the pressure and the temperature. So we do want to be on the lookout for that. Do I have pressure and temperature? That's going to enable me to use the ideal gas law to plug it in with my stoichiometry. So what information is there? We can see we need to be given mass of the other thing in our reaction, right? And that's going to become where the reaction comes in. We know that in order to do stoichiometry, we need to use moles. So we're going to need to figure out the molar mass of our NaN3, which we can compute using periodic table. I'll plug that all in, be good to go. Okay, so we know we're going to use the ideal gas law here, where that's going to be one of our kind of big plugins. We know what we want to get out of that is volume. So N, R, T, and P, number of moles, R, T is temperature, P is pressure. Those are the variables we would need to plug in. And so we know that the pressure and the temperature were given. The pressure was 1 atmosphere and the temperature is 298 K. We want to be careful. It's 25. We've got to add up into Kelvin. But the number of moles, we can see that's what we don't have, right? We do have R, that's our gas constant. But that number of moles of N2 isn't given in the problem because it's being created in the chemical reaction. And really what the question is asking is how many moles of N2 are we going to make? So we can use stoichiometry. We know we started with the 130 grams, right? That was given to us. From that, we can use the molar mass of the NaN3 that we have right here. I computed that myself, looking at the periodic table of what the molar mass of sodium and the different nitrogens are. So I can get that 65.01. I turn it into moles. Then you'll note I'm using the reaction coefficients, the 3 and the 2, to go into moles of N2. So if I have if I react 130 grams of the NaN3 in this reaction, I will produce the 3 moles of N2. So the 3.0 moles of N2 will be produced. Normally, or previously in stoichiometry, we would have then used, say, the molar mass of N2 to get a mass of the N2. And you can do that if you want us to know the grams of N2. But because it is a gas, it's much more common that we use instead describing the amount of gas using volume, just because it's been useful than saying it's 50 grams of N2 gas, because it's kind of hard to think about what that is. So we've got the moles. What we can do is we can plug that in, right, into using our ideal gas law. We can plug in the moles that we have there. We can plug in the ideal gas constant, right? We can always just look that up, the temperature, and then the pressure, and then we get the volume out of it, right? So we see that everything else cancels out, atmospheres, atmospheres, moles, moles, Kelvin, Kelvin, and we are left with liters. So really one of the purposes of going through this example was to show the primary utility of gases. We can see that the density of NaN3, we can use that, figure out that 130 grams is 70 milliliters. So in your airbag, you have the NaN3, the sodium azide, just sitting in your steering wheel. It's in your steering column. It's a very small volume that's in there, right? Say 70 milliliters. And when it activates, when it undergoes this reaction, you produce gas. And gases are mostly empty space, so they take up way more volume. You still have the same amount of mass. In fact, you lose some in going into the sodium that's still in there. But you do produce all this gas, and it's now 73 liters of nitrogen gas. That is so much gas, right? In such a huge volume. That's why your airbag inflates immediately to fill all of that up. It ends up going to a higher pressure than 1 atmosphere. And so you fill up this huge airbag, you fill it up with all this energy or all this gas, and then importantly, so it fills up really fast. But then because it's a gas, it's compressible. So, you wouldn't want to use like a water bag for crash safety because one, you'd have to store all that water. It won't expand to fill the airbag or the water bag, right? You'd have to have a bunch of water in your steering column. And then when it went into the water bag, when you as a passenger hit it, it wouldn't have any give, right? It doesn't compress at all like a gas would. So that's why we use gases. They will expand to fill, and then importantly, we can recompress them. And we use sodium azide because it reacts really quickly, and nitrogen is very undangerous as far as the gas goes. Let's look at another example. Humans gain usable energy via the combustion of glucose, C6H12O6. What volume of CO2 gas is produced when 1 pound, which is 454 grams, of C6H12O6 is burned under ambient conditions, which is 1 atmosphere and 25 degrees Celsius? And the molar mass of C6H12O6 is given. As a reminder, when we're going through these problems, if we're dealing with any of this, I'm going to give you the molar masses when we're doing stoichiometry problems. To kind of, that's not really the purpose here. If you need it, it's not necessarily, the purpose isn't for you to compute molar mass. The purpose is for you to see if you can use molar mass correctly in stoichiometry context. Okay, so we are looking for a volume of CO2. We're making it in this reaction, and so it's going to be based on the reaction of the C6H12O6, right? Where we are burning a certain amount of C6H12O6, and we want to know the volume of CO2 that we make out of it. And so in order to do that, that's going to be our stoichiometry process. We know that this molar mass that we have right here is what we start with. We divide by that molar mass to turn it into the moles, right? And then that's moles of the C6H12O6. What I really care about was, again, the volume of CO2. So I'm going to get it into moles of CO2. And I can see I have the 6, which comes from that right there. And then the 1, which comes from the coefficient that's missing in front of there, the 1, the implied 1 that we have right there. Again, we use those coefficients. And we can see that we come out with 15.1 moles of CO2. We could, again, convert this into mass if we wanted, but because it's a gas, we generally care a bit more about its volume. So now that the whole point of figuring out that moles of CO2 is we want to turn it into the volume of CO2, which is always going to rely on the ideal gas law, right? We're taking moles and turning it into volume. That's a different type of measurement about the same sample of gas. In order to do that sort of change of variables, you're always going to need to be using the ideal gas law. So we're looking for volume. We know that the pressure we're given is 1 atmosphere. The temperature, we're 25 degrees Celsius. Turn it into Kelvin by adding the 273. And then the number of moles is what came out of stoichiometry, right? We got 15.1 moles of CO2. So we can plug all of those variables in, right? We had our pressure, the number of moles. R is the gas constant. We always can just look that up. And then the T is the temperature. We can rearrange it, divide the 1 atmosphere. We can see then that those moles cancel, the Kelvin cancel, and the atmospheres cancel. And we are left with 369 liters. So when a human loses weight, you do it by burning, say, glucose, by doing exercise, by burning that. And you really lose, the primary way that you lose that mass is by breathing it out, right? You breathed in oxygen, O2, you breathe out CO2 gas. So that gas has a little more mass to it that you are breathing out. And for every 1 pound of C6H12O6 that you burn, so 1 pound of mass off of you, that is 369 liters of gas that you are exhaling. That is just blowing the fat away.